Hey everybody, good morning. Welcome to lecture 6. In today's lecture, we're going to learn about another very important Python package named pandas, which is for manipulating tabular data. In the previous lecture, we've learned about NumPy, which was very well tuned to do matrix operations, linear algebra, multidimensional matrix manipulation, and things like that, and a lot of functionalities that are built around mathematical operations for matrices, basically, and for arrays. However, we don't always deal with matrices. We don't always deal with linear algebra. Most of the time in most data science projects, what we're dealing with directly is tabular data, basically. So for these situations, we have a much more flexible and much more optimized version of NumPy, basically, for tabular data. For example, in NumPy, we dealt mostly with, not mostly, almost always, we dealt with numbers inside of an array. However, with tabular data, you might want to store strings, you might want to store times and dates along with numbers, and you want to have certain capabilities for the package to be able to deal with those kinds of data. For example, you might want to manipulate all the strings inside of a table. You might want to clean up some data. You might want to wrangle some data. And these kinds of tasks are either not possible in NumPy or are very difficult to do. And you can think of pandas as something quite like Excel, but with a lot more functionality, with a lot more, with much greater performance. So you remember in Excel we have like columns and rows, and you can also have like column headers and also row labels and things like that. These kind of things are not possible in NumPy. In NumPy, you're just limited to numbers and indices. But with pandas, we have all that functionality built around this table object. So let's get started and see how it looks like. Okay. So one way to think about pandas is that it's like Python's version for dplyr that you've learned about in R. So there is some parallel in R for pandas that might be helpful to wrap your head around what pandas does in Python. Okay, so to get started, I'll introduce two kinds of objects that pandas provides us with. The first is a pandas series. The second is a pandas data frame. So these are the two main objects that we work with in pandas. Just like in NumPy, we had this object ndArray, which came with like a lot of methods and a lot of specific ways in which it handles the data. Again, same is true about pandas. So developers for pandas came up with these objects that provide us with certain capabilities and functionalities that allow us to be able to handle tabular data in the most optimized way that's possible. So, what's a series object? What are its properties? So a series object is basically quite like a NumPy array, basically a NumPy vector. So it's one-dimensional, and it contains data only just one dimension. Again, something quite like a vector, with the difference that it also has a kind of a row, not a row exactly, but a kind of additional data attached to it, which is called an index. So an index is just a label for the data that you have stored inside of your pandas series. Again, to show its parallel inside of NumPy, it would be like thinking about the NumPy vectors, the data that we store in it, and the indices associated with those data points. So in NumPy, you have a bunch of numbers, and you have indices corresponding to those particular locations where the data happens to be stored. And the same goes here with pandas series. So we have the data, and we also have labels associated with those data. You can think of this way as storing things like inside of dictionaries instead of inside of lists. So with NumPy, again, we have data stored inside of a vector, and then for each data, we have an index, which we can use in order to retrieve that data. Here, instead of an index like a numerical index, we can have an index that's numerical, or that's string, or something else. So that's basically what pandas series is. Okay, so like you can see here, this series has, the data is string values and the index is numerical, just like in NumPy. But here the index is like characters, which was something that wasn't possible with NumPy. And again, here the index is numerical. We can retrieve those items using those index values, and you can see that the data is stored. Can be lists, can be strings, can be anything that you like. And here the index is a specific type, which is a date-time index, basically. And we'll learn about this in the next 2 lectures, not in this lecture. So right away, you can see that pandas series are more flexible in order to basically name the data that we have. We can name it with numbers, or we can name it with date times, we can name it with strings. So it's much more flexible. Okay, so let's see how we can create this series object. In order to do this, just let me mention that I've imported pandas as PD, the alias is PD, and that's just a convention. And in order to create a series, you can call pd.series, and then here you can specify the data that you want to be stored inside of the pandas data series. If I run this, the output looks like this. So you can immediately see the data type for this kind of vector-like thing. You can see the data, and you can also see an index. So if you don't provide an index to a pandas series, it will automatically create a range index, starting from 0 all the way up to as many elements as you have. Again, this is like the default behavior is just like what NumPy does for us. Okay, but the thing is we can create our own custom index. So here, this is my data, but associated with each data point, I want to have an index that's a character. So A, B, C, D, E in this case. And you can see that the index column here changed from numbers to these characters. Okay, so this one over here was pretty much like what we had in NumPy before, and this one over here is a little bit different. We have used different names for our data. Yes? What if you have more data other than the index? I think, okay, question is, what if we have more data than the index that we provide? I think we'll get an error. Let me just try. We should get an error. Okay, yeah, we get an error. Okay, and there are various ways to define a pandas series. Going back to lecture 3, your favorite lecture, we have alternative ways to create our pandas series data type. So we can input the data right away as a list of values, or we can read the data from a dictionary that contains key value pairs, and the key is going to be interpreted as the label, the value is going to be interpreted as the data. So this is an alternative constructor for this series data. You can see that A is associated with 10, and here A is in the index, 10 is the data, and so on and so forth for the other data that we have in this series. You can also pass a NumPy array to your series to create your series. So here I'm generating random numbers, normally distributed random numbers, 5 of them, and I'm passing this to pandas series, and you can see that it handles it without any problems. Yes?
Just a question. I see that they say D-type, float 64, or index 64, depending on the context.
Right.
Is it a special type of float, float 64?
Great question. So what you see here, yeah, float 64 here and maybe int 64 over there. So you might remember that in Python we didn't have these types. We only had int or float. This is because pandas is built on top of NumPy. And in NumPy, we actually have these data types. For example, in very computationally intensive projects like most machine learning projects, it's not really memory efficient to use float 64. So in those instances, we use float 32 to save memory, save computation time, and everything. This is why NumPy provides these alternative types of integers and floats. Yeah. Any other question? Okay. And similarly, we can also pass just a scalar to a pandas series. That will obviously be a series containing only one value. This is just to show you that there are many different ways in order to create our pandas series. There's some echo here. Okay. And here, I'm using a scalar, but I'm providing more indices than data. And in this case, we don't get an error. The scalar value will just get repeated for as many index values as we have, for as many labels as we have. Okay, so we covered a few ways to construct our pandas series object. Typically, we usually don't construct series like that. Series come up when we create another object called data frame, but it's just to give you an idea what these objects look like. There is an important property of a series, and that's that we can assign a name to it. So for example, here, my data is just random values, and I'm assigning a name to my series as well. So you can see that here, I can see this name. And why is this important? It's because when we create our tables, then these names will actually be used, for example, as column headers. So this column has this particular header, and that header will be interpreted by pandas as this name over here. But we'll get to that. So for now, just remember that we can also assign a name to this vector-like data type that we have. Okay? And you can retrieve that particular name, that attribute, using s.name, something we've learned when we covered classes. And you can also rename it, simple. Okay, now one question that comes up is we have these index values and we have the data. Retrieving the data should be easy because we just look at the series itself, we get the data back. But in order to retrieve the index values, because we might need them, we can type s.index, and here we go. It tells us that the index was created from this range index object, just like in Python we use the range for loops. So it's an object that has this certain property, starts from a number, ends at a number, has a certain step, and pandas loops through that for as many data values that you have to create your index. There is this convenience method for series, as well as for data frames that we learn later on, to NumPy, which basically converts your pandas series to the good old NumPy arrays. Okay, and you can see that it basically ignores the index. Look at this one here, and you can see that because NumPy likes to see homogeneous data types in the vectors, it gives a data type of object to say that, this is not good. This is the kind of object that can't interpret that as just numbers. Okay, question? Yes, that's possible. But it's not something that people typically do with data frames. But it's possible. Yeah. You can basically transpose a data frame and assign the index for the columns, assign them to index for the rows, and vice versa to basically get what you want to get. But this is, again, not quite a common operation. I don't know if in R you have yet talked about this, that usually the way that data is stored in a table is that we have observations per row and we have attributes per columns, and it's not really common to have the opposite case. Yes?
Would you still be able to use the integer index once you have resolved the binding?
Okay. Great question. Will we be able to use indexes with these series data type now that we have these labels? So I'm getting to that in a moment here in this section. Yes?
Shouldn't NumPy array only allow the same data type in the
Yeah. So the question is, shouldn't NumPy arrays only allow one certain data type? NumPy likes to have a certain data type inside of the array in order to improve performance. However, if you force it to use a mixed kind of data type, it doesn't complain. It just assigns a data type of object to say that, hey, it's a general object, a mixture of objects, different objects. Yeah. Okay, so now let's talk about how we can retrieve data from these pandas series. So here I'm creating this S series, and it contains numbers from 0 to 4. Here the data is numerical and the labels are characters. Okay, a little bit different from previous cases, and you can see the data type is automatically inferred. Now let's retrieve some items. So here I can use numerical indices in order to retrieve that data. And here, for example, I want to retrieve elements at index 0, so the first one, the second one, and also the fourth one here. And this is why I'm providing these indices inside of a list to say that I want to retrieve multiple values. And we will get our data back by using this kind of indexing. And slicing is also possible, just like we've learned in lists or in NumPy arrays, items 0 up to 3, and we get those back. Indexes 0, 1, and 2, excluding 3. Okay, so this is the usual stuff that we're used to. Okay, now, one thing that's different about pandas series is that if you provide the labels to them inside of square brackets, they behave like a dictionary. So in dictionaries, inside of square brackets, we supply the key, and then we get back the value. So here it works quite in the same way. So A corresponds to 0, that's the key, and that's the value. Okay? And we can also provide multiple keys, or let's say multiple labels or multiple indices, and we get the data back for those indices. Okay, and we can also do slicing using those labels. So note that when we do slicing in this particular way, the last item is also included in what we get back from that. There's this tiny difference, and the way that you can tell whether this behavior is what you will get. You can notice that this is not a numerical indexing. This is a particular type of indexing that belongs to the way that pandas handles things. Okay, so in dictionaries, this way of slicing is not possible. Actually, we don't have slicing for dictionaries. Okay, but this is possible in pandas only. One thing that we can do, similar to dictionaries, is that we can check whether a certain label exists inside of a pandas series. Okay, so for example, we want to check whether C, this character C, exists as a label or as an index inside of S. And it returns true because we have C in there as a label. But note that we can't check for values inside of C in this way. Okay, so for example, 1 in S doesn't work, although we have the value 1 here, but it doesn't understand because 1 is not a label. And we don't have Z in here as a label, so it again returns false. Okay, now, so I've redefined my series S here so that this time the data are these characters, these capital letters A, B, C, D, E, and the index are just numerical indices. Okay? So let's say that I want to retrieve the last item. Okay? And based on what we just learned, if we type S minus 1, that should retrieve the last item for me, but it doesn't work. And the reason is, whenever the index is numerical, pandas actually looks for that particular value inside of the labels. It doesn't interpret that as a numerical index. It interprets that as a label, like a key in a dictionary. So you have to be careful about that. When you get this error and your index is numerical, you don't get what you want. This is because it's not going to be interpreted as a numerical index. Any questions about this behavior? Yes?
You mentioned the data is stored in the NumPy array, right? I was wondering if the indices also stored in the array?
I don't think they're directly stored in NumPy arrays. They have a particular data type called index. It's called index itself, inside of Pandas, which handles the index data. I don't know what is the underlying implementation for that one. Yeah. Yeah.
So you were saying if I'm slicing with the strings or whatever, it's included. If I slice with an index, the last one, will that be included in Pandas or not?
Yeah, so again, if it's a numerical index, and that's the behavior that NumPy provides us with, like the functionality that NumPy provides us with, then it's like the normal index behavior. The last item is not included. But whenever you're using this Pandas capability to index into a series or in a data frame, using the labels, then that item will be included.
In general, if we want the last thing for NumPy, do we use like len s then? If we want to index the last one?
If you want to index the last one. Oh, yeah. Sure. Yeah, okay, no, I don't know if lenx works in this case, I'm not sure, but we will learn about like standard ways in Pandas to retrieve items either using indices or using labels. So there are standard functions for that. Okay. In general, we'll get to that in a bit. In general, I don't really quite recommend this way of retrieving data from Pandas series or data frames because it can be confusing. So in Pandas, there are two functions called lock and ilock, and they are those that kind of standard way of accessing items. Yes. Sure. Can you repeat your question, Sai? Yeah. I use double brackets. Oh, that's for when we want to specify multiple labels that we want to retrieve. For example, here we have this double because this square brackets tells Pandas that we are looking for certain indexes or certain like items or labels. And here I'm telling Pandas that retrieve these particular items for me, that they might not be like sequential. Okay, I take one from here, one from there, one from the middle, so I have to provide the labels inside of another set of square brackets. If you choose keys that are not, so in that case, we look at the first item and then the last item, and then Pandas retrieves all of the items in the middle. Yeah, so that basically works as a range kind of thing. Yeah. Okay. All right. Okay, so one other strange behavior is that, not so strange maybe, is that if you have multiple labels for your series, for example, here I have the label A for several items, if you try to retrieve those items using that label, all of those items will be retrieved for you because they all have this label A, so that might be expected. And this is just something to note. And one other thing that we learned about in the last lecture is that we can also do Boolean indexing, meaning that we can, with logical conditions such as this one, so s greater than 1, it means that look at s and then apply this condition onto each item and return a Boolean value to me inside of another series. So if I run this, let me see. Okay, so, okay, sorry. So let me see. Okay. S here, and then S here. Let me just change these names. Okay, and now, okay. So now you can see that in another series, it tells me, okay, this condition for the first row was false, for the second row was false, but for the last 3 rows, it was true. Now, just like NumPy, I can take this condition and pass it directly to my series in order to retrieve only those items for which this condition was true. So here, if I do this, you can see that I get back these values. So A equals to 2. Let me see. Yeah, so here, this one label is equal to 2, not all of them, and it only retrieves that one for which this condition was true. That's why you can see A. and then B and C as well. Okay, and I can also do something more complex, like only retrieve those items for me for which like their value is greater than the mean value, and we can also do that. Again, something more complex would be to say that look at S and compute the remainder of its division by 2, and only return those values back to me when the remainder is 0, meaning that those return back to me the values which are even numbers. So here, this tells me that this item was an even number, this one was an even number, as well as this one. And then I can pass it to S itself to retrieve those items. Okay, so I created my mask, provided it to S as a Boolean index, and then it retrieved those items. And I can also negate that to retrieve only the odd numbers. That also works. And you might say in this case, why am I using this tilde notation instead of not? Because we've learned that not can be used to negate a Boolean condition. That's because this condition over here is not a regular condition, it's actually a series. So not doesn't know how to work with that. So if we do that, it will give us an error. But here, this operator in pandas works to negate values inside of series. Okay, any questions? Okay, great. Now let's move on. All right, so in NumPy, when we try to do mathematical operations between arrays, we added one array to another array, and then those operations were used to be done in an element-wise manner. So based on index values, basically NumPy grabs items at the same index values and then adds them together, multiplies them together, divides them by each other, and so on. In pandas, these kind of operations are done based on, again, based on indices, but in this case, these indices can be non-unique, and they are labels that can be strings, can be numbers, anything. And that has some implications associated with it. For example, if we have a series like this, data 0, 1, 2, 3, index A, B, C, D, and then here we have another series for which we have an extra element E, but we're missing the element at index A, okay? In that case, when we add those two series together, what we get is the union of both. However, for this one, we get NaN, meaning not a number, meaning that Pandas doesn't know what that could be because that's unknown for the first row, and for the last row as well. So Pandas does that, performs those mathematical operations on corresponding elements with similar labels. And for those items that do not exist in either of the series, you'll get back another number. So let's see that in action here. That's the first series here, A, B, C, D, 0, 1, 2, 3. That's the second one, 10, 11, 12, 13, just like over here. And notice that the label here is different, E, and I don't have A. And when I do this, I'll get back something like that. Okay, one thing to note, the data type just changed. So both of those series were integer 64. However, in this case, I'm getting float 64. Do you happen to know why that's the case? You're not expected to know, we'll get to that, but just, do you see something that could have caused this behavior? Yes? Exactly. So the problem is with the NaNs or not the numbers values. These are implemented using NumPy. np.nan is a particular kind of value in NumPy that is of type float64. Happens to be of that type for some reasons that we don't go into the details of. And that's why when Pandas sees those NaN values, it kind of forces everything to be of the float64 type. All right, and again, just like the addition, all kinds of mathematical operations can be done on series because these are, again, this is based on NumPy, so anything that's possible in NumPy is also possible with Pandas series. You can raise this to the second power over here, or you can exponentiate these values. Anything that you like, you can do with them, like in mathematical terms. And here, let me just show you all the methods that are possible, that are implemented for Pandas series. There are a lot of them. There's a whole a very comprehensive documentation about these methods on Pandas website. You can look into them. This is just to show you that there are a lot of capabilities associated with this simple-looking data type. And we have already used some of these capabilities. For example, we have used this mean method, or I think we used the min or max method as well. This is just, again, to show you a list of all the methods that are implemented for Pandas series. Okay, just a couple of examples. S1 was as we define it here, and we can do S1 dot mean, okay, returns the mean values, S1 dot sum, sums everything up. This particular method, as type, converts the data type inside of the Pandas series to a particular data type that you provide. And here, the original data type was int64. Here, it becomes float64. And we can also chain multiple operations together, just like something that we might do in R using the pipe operator. Actually, the pipe operator, I guess, was updated last year to something like that. Is that right? Yeah, okay. Yeah. Okay, this used to be experimental, but I guess now it's part of R. Okay, so if we do something like that, S1.add, so adds this value to all elements, then raises this to this power, and then converts everything to integer, and then takes the mean. So pretty much like in R. Okay, so let me see what we have left for series. Not so much. So let me just quickly cover this part, and then we take a break. So we have discussed the kind of data types that could be stored in Pandas series. And again, this is something that's inherited from NumPy. So here, if I define my series like that, if you want to know what is the data type, you can do it by typing x.dtype, and that will tell you what is the data type of the value stored inside of that series. And remember that for strings or mixed data type, if you inspect the kind of data type of that series, you'll get back object. That's how Pandas treats strings. It recognizes them as being objects, but you don't need to worry about that. The kind of operations that are implemented for strings are still super fast. They are very performant. It's just the way that Pandas shows us the data type. There is a newer string data type in Pandas that is not yet kind of mainstream, that is not yet quite used a lot by developers, and there is not really that much performance difference between these two data types. So if you have strings inside of your Pandas series and you see object as a data type, you're safe. Don't worry about that. For this current version, according to Pandas documentation, there is no significant performance difference for vectorized operations on those data types. Okay, and again, if we have mixed data for our series, just like NumPy, we obviously get back dtype is equals to object because it's a mixture. Okay, and here I'm just trying to look at the kind of data that I have in this list. And map, again, is a method that's implemented for Pandas series. Basically, what it does is that it takes this function that you supply to it and then applies that onto each element inside of your series. So here I'm taking this function type, and remember not to provide it like that, because here we just want to grab the name of the function. We don't want to call it. And map takes it, applies it onto every element inside of X. Okay, so you can see the first one is a string, the second is an integer here, and the last one is a list, which is why the data type becomes object. Here I just have a piece of code to show you the memory usage for different kind of data types. Here I have all integers over here, 152 bytes, and you can see as soon as we have objects, suddenly the memory usage jumps to a much higher value because there's a lot of other information that pandas has to store for you in order to represent objects. And that's why you see, for object, you see 258, for integer, 152, for integer 8, a kind of smaller integer type, you get 131. This is, again, not detail that you need to be concerned about. Just know that for objects, we need a lot more memory. Okay, so something we discussed was this np.nan, np.not a number. And this is a particular value defined in NumPy to represent nulls or something that's unknown, something that doesn't exist. And it's defined using this np.nan. And if we inspect its data type, we see floats. And this is why we saw the behavior earlier. So if you have something like this, everything is integer here except for this one, and it converts everything to float 64 because of that. There is one way around this problem. So if you have all integers and you have some NANs inside of your list, some unknown values, you can actually use this particular data type that's defined by pandas, and it starts with a capital I instead of just lowercase I, and it treats those unknowns in a particular way. It treats them as integers, and you can keep the original data type that you had for the series, which was integer 64. So this is again implemented by pandas. This is something you can use. If you happen to have a lot of unknown values inside of your integer columns, this is something that you can consider. Okay, so the next section, we'll move on to pandas data frames, but before that, let's just take a break for a couple of minutes. All right. So, pandas data frames, the kind of object in the pandas package that you're probably going to be using for the rest of your data science career until something else comes about. So this is a pretty important topic, one of the most pretty important object type, one of the most important ones in today's data science. So what is a data frame? Okay, we have learned all the basics for it. A data frame is nothing but a collection of pandas series. Series were vectors, just one-dimensional data, and if you stick them together side by side, you're going to have a data frame. So here we have series 1, series 2, series 3. We have combined all of them into one object called a data frame, and there we have it. We have a table that still contains all the data for all of those series 1, 2, 3, but it's represented now as a two-dimensional object. And notice that the index values, the row indices, are the same for all of those series. And if you combine series that have labels that are different, they will be treated in the way that we just saw. So pandas just gives you NaNs for the values that are missing, for the values that we don't have the data for. Okay. Now let's see how we can create data frames. Again, just like series, we have a lot of different ways to create our data frames. One way would be to provide a list of lists, basically rows and columns, directly just using this syntax, double square brackets. And there we have it. So this is the data, what you see in here. And notice that Pandas gives you this nice formatting of the output. So this is the data. What you see at the top is the series names. So the names that I discussed in the beginning, that I talked about, I said that with each series can also be associated a name, and those names will be used as column headers. And here we have the row labels or row indices. So 0, 1, 2 over here and 0, 1, 2 at the top, those are the indices. Okay? And this is the data. Now, an alternative way, not an alternative way, to provide some more metadata for our table, we can actually name those rows and those columns by providing index equals this and columns equals that, and then it names those rows and columns accordingly. So R1, R2, R3, those are not the data, those are the indices. Column 1, C1, C2, C3, again, those are column headers, not data. Okay, one alternative way to create the same Pandas data frame is to provide dictionaries to the data frame object, for which the key is the column header that we want to use, and the values are basically the data that I want to store inside of my data frame. So here, I'm using C1. Again, that's the key. That's going to be the column header. C2, that's the key. That's going to be the column header, and these are the data. And I'm also specifying an index for my data frame. Okay. One other way. And here, I'm providing the data as random values generated using numpy.random, and I'm creating the indices and column headers using a list comprehension, because I might have 1 million rows, 1 million columns. It's not convenient to type them in, those names of the columns and rows, so I just create them using a list comprehension, and there we have it. Again, for row labels, I use the index parameter. For column headers, I use the columns parameter. Okay. Okay, one last way to construct these data frames is to provide the values like that. So inside of a two-dimensional NumPy array, I basically specify the rows and columns just as we are used to from lecture 5, previous lecture. And that again creates the data inside of the data frame for me, and because I haven't given an index or a column header name, I'm getting the default, which is numbers starting from 0 all the way up to as many rows as columns that we have. And here is just a summary of the various ways that I can define a data frame. And usually we don't create those data frames ourselves like that. We usually read data from a file or from a URL. So it might not be that helpful to learn all those methods, but it's just good to know that they're there. If you need to use them, this is how you can use that. So before going into indexing and slicing, any questions about how we construct data frames or what data frames are in general? Yes?
When you create a data frame from, say, from two series, is it required that both of them has the same indices?
Great question. So when we create a data frame from two series, if they don't have the same labels, what happens? Is that possible? Yes, that's possible. But again, just like when we added two series together which didn't have the same labels, Pandas handles that by putting NaNs for those values that it doesn't know about, and for common values, common labels, it just fills it with the corresponding values from the two series. Does that make sense?
If there's no common labels,
Okay, so you'll get a lot of NaNs in your data frame. So like a matrix that's filled with NaNs on 2/4 of the data frame. So a lot of NaNs. Okay, any other question before we move on? Okay, so just like I mentioned in the beginning, I showed you a couple of ways that you can retrieve data from a Pandas series by whether by providing the row labels or item labels, item indices, or by numerical indices. But I told you that might lead to some confusion. It's not really very obvious when you see that in the code, but Pandas, thankfully, provides some standard ways in order to retrieve data from data frames. So the first way is what I showed you with square brackets. Again, I don't recommend using that all that often. So here, okay. So we have, a heating problem here. Okay. So here's my data frame. We have name, language, and courses, and these are different instructors that I define in this data frame. Okay, now let's start indexing with square brackets, just to learn that this is one way that it could work. Okay, so if I provide the name of the column here, I will get back that column. Okay, this is like the kind of, we could say, the expected behavior, because it acts like a dictionary, and then when we provide the key to it, it returns the values to us. Okay, and notice that what I get back is a Pandas series. It's not a data frame. Okay, but if it's absolutely necessary to have a data frame object, I can wrap that column name inside of another set of square brackets, and in that case, I'll get back a data frame, and you can immediately tell inside of Jupyter Notebooks by looking at the kind of formatting of the object. This is a nicer formatting. It's not plain text, it's HTML, and you can see that, okay, this is a data frame. But if you're curious, you want to have a more robust way of doing that, you can also check that by using the type function, and it says data frame. Okay. So here we just retrieved one column. If you want to retrieve multiple columns, again, just like series, we have to provide the labels inside of square brackets. Okay. So names and languages only, and in this case, the only possible way to return that data is inside of a data frame, and we'll get a data frame. Okay, so here the confusion, I guess, begins with this way of indexing into Pandas data frames. So df, and inside of square brackets, if I supply 0, it doesn't work. Okay, but slicing works. So if I want to grab rows, the first row and the second row, this syntax works. It's very confusing. Even to me, after a few years of working with Pandas, I still have to refresh my memory to see which one of these methods actually work. This is why I don't recommend it, but we'll get to more standard ways in a bit. Again, slicing works using indices, but single items cannot be retrieved by just single numbers. Now, the methods that I like very much. So indexing with this .loc and .iloc functions. So Pandas has these two methods. Basically, one is for retrieving data using integer values, just like what we had in NumPy. So you have numerical indices, You provide them to iloc, and it gets the values back for you. And this is why you see this I, meaning that it receives integers, integer indexes. And here we see df.loc, which is another function in pandas that retrieves items based on labels. Okay? So again, it's very, the applications are quite separated. It's quite obvious which one to use. So this is why I really like these two methods over just a single set of square brackets. Okay, so this is my data frame over here. Now let's give it a try. So df.iloc0 behaves just like NumPy. It retrieves the first row for me. Okay, in NumPy, even if your array is two-dimensional, if you provide just one index, then it retrieves all of the items in the first dimension for that index. Okay, now let me grab these two first items using iloc. Again, works as expected, just like NumPy. Let me do slicing over both rows and over columns at the same time, and it works. 2 to 5 and 1 to 4. And notice that here I only have one item after 2 and only 2 columns after 1. This is why I see this value being retrieved. And I can also, again, supply a list of integers, a list of indexes in order to retrieve items that do not belong to like a one range of values. So this retrieves 0 and items stored at row 0 and 2 and columns 0 and 2. Okay, now let's take a look at .loc, which can retrieve items for us based on labels. This is one of the main differences between NumPy arrays and pandas data frames. So suppose that you have a large data set that's stored inside of a CSV file, and it's not uncommon to see 200 columns. And then when you have 200 columns, it's not really so easy to remember which column corresponded to what data. So in this case, the column headers are like lifesavers. That's why you want to retrieve items by referring to the column headers. Okay, and same goes for row labels. This is why this loc function comes in very handy. Because you might say in this case, okay, when I have integers, why should I use labels? Because you're going to see how helpful it can be when you have working with large data sets. Okay, here I want to retrieve all of the rows and only the name column. There we go. Because it's just one column, I get a series back here. Here, all the rows and all the columns from name all the way up to courses. And again, notice that that last item is also included. This is the pandas way of handling label indexes. And again, I can also provide a list of labels that happen to be at different places, not just in a sequential order. So I can provide this for the labels, for the rows, and this one for the columns. So the first element here corresponds to the row labels. The second one corresponds to the column labels. And if you do this, it doesn't work, def.loc 0, because 0 is not a label. Okay, so just like series, I can also inspect the index, which in pandas lingo, we always call row labels index, and we call column headers just columns. You'll get used to it. I know it can be confusing, because they both are just labels, they both are indices, so this is the way that pandas defines them. And you can actually see that the data type for both of these is actually an object defined in pandas called an index. So df.index, df.columns, whenever you want to grab the column headers, whenever you want to grab the row labels. All right. Now, suppose that there's a situation in which I want to use a mix of labels and integers. So for some particular reason, I want to take a slice of, for example, a slice of the rows, but I also want to be able to provide a column header instead of the index. So that's possible, and we can do it using this like clever syntax. We can actually always index into this index object itself and grab the label for that one. So suppose that here I want to grab the row stored as the first row. Okay, so I can actually go into that index object, grab the first item, and supply it as a label here. Okay, because here what I should have is inst1, right? So instead of giving that directly, I say, hey, go inside of df.index and grab that first label for me. So in this way, I can actually mix those two methods with each other. Okay, so again, if I do something like this, 0, it grabs that first low label for me. Okay, so in this way, I can do this. And again, similarly for columns, this also works. And notice that I'm using .look in both of these situations. Questions? I think you agree with me that iloc and loc is a much more intuitive way of retrieving values from a data frame. It makes a lot more sense. I for integer, whenever you have integer indices, and loc whenever you want to retrieve items using their labels. Yes?
When we are talking about column names, if they were, for example, an integer and all of them were integers, when we're searching, it will find it as strings still?
Yes. Okay, so that's a great question. If we have a mix of integers as well as strings for the column headers, when we try to retrieve those items using like the number, if we're using loc, it will look for the value itself. It doesn't interpret that as an index. But if you use iloc, then it will search for an integer inside of there. Okay? Yeah. So if you have an item with label 5 stored at index 100, you can't retrieve that 5 by saying 5 inside of iloc, because that looks for the integer, not for the label itself. Yeah. There's a distinction between the two. Yeah. Yes?
So what you think is that iLog actually takes an integer rather while log take the label.
Exactly. Yeah. So iloc always takes an integer. Loc always takes a label. That label can be an integer. Okay? It can be confusing at times. The label can be an integer, but it's not the index position. It's just a label, and it could be like an unordered mix of integers. It's still a label. Okay. All right, so just like we have Boolean indexing for NumPy arrays, for pandas series, we also have Boolean indexing for data frames, and that's actually a very useful way of filtering the data inside of a pandas data frame. So here, let me just show you the data frame again. I'm saying that, hey, look at the courses column, this column, and retrieve those, and tell me which one of these items have a number in them greater than 511. Okay? And if I do that, you can see that it returns to me this Boolean series, and it tells me the first one is false. That's not greater than 511, but the last two are. Okay? And now that I have defined my mask, basically, the way that I want to mask some certain items, I can provide that mask directly, for example, to .loc. Okay? So I say that only return these rows that satisfy the conditions inside of that mask and all of the columns. Okay? And I can have different types of conditions. For example, here, my condition is only retrieve the rows for which column name is equal to Arman. So that's my mask, and that's only true for one of the rows, as I can see over here, the first row, and I can provide that with my .loc, and here we go. Okay. So notice that here I'm using the mask on the rows, okay? I can do the same thing with the columns, but again, just like we discussed in the beginning, because in the particular way that we have, like, we want to organize data, I think you've heard about tidy data, right, in your R course. So tidy data refers to the situation when you have observations as rows, attributes or variables as columns. In that case, we usually don't do masking on the columns quite that often. So that's why I'm only showing here masking for rows. So basically, I want to apply a filter on a column, and retrieve certain rows. I usually don't want to apply a mask onto columns, a mask onto rows and retrieve certain columns. That's the difference. Okay, so iloc and loc. To recap, iloc receives integers, looks for particular positions. Loc looks for particular labels. Now, there's another way of retrieving items from a data frame, and that's by using this function called .query. So if you're by any chance familiar with databases in SQL, this syntax will look familiar for you. If not, we'll learn that in block 3 in the databases course. I'll teach you about SQL and the similar syntax. But for now, if you want to do some simple filtering on the columns, this is a more succinct way of doing that. So here I'm saying that retrieve those rows for me where course number is greater than 511 and language equals Python. And you can see that the syntax is very easy to read, basically. And compare it to this syntax that achieves the same thing. So that one at the top and this one using the loc function. When you have multiple maskings and all that Boolean stuff going on, this query function can come in very handy. Yes?
Is there any way to get autocomplete in the query string?
No, unfortunately no, because that's just a string, and it then goes into a parser inside of Pandas data frame that interprets that into something else. Yeah, but there's a comprehensive documentation page for .query that you can look at. It's actually not that complicated. There's just a couple of operators like the and, greater than, equals, and stuff like that. So pretty limited. Okay. Again, you can do this just by creating your mask like that, and I'm gonna move that to another line and type mask here to make my code more readable, because previously it was pretty ugly. So right now it should be a little more readable. Okay, so both of these codes achieve basically the same thing, and you can see that the one at the top is more readable. All right. Yeah.
Let's say if you want to format within a range of the data frame, let's say from row number 3 to number 5, is that something you have to put down the data frame first, or is something you can do with the query function?
Okay, so you want to grab certain items at certain locations inside of the data frame.
Right.
Is that right? Okay, for that case, I've never seen it being achieved using the query function. I think you have to do that with iloc, if that's the case, if you want certain numerical ranges. Yeah, this is the most common use case where you have like a column and you want to look into the column values for your filter. Yeah. All right. One other tiny thing here is that if you want to use one variable from your Python environment, for example, here I have course threshold equals to 511, and if I want to use that inside of my query, you can prepend that with this @ sign, and then Python replaces that whole thing with the value, and then you can use that inside of your query like that. Okay? All right. Here I have an indexing cheat sheet kind of thing. You can see multiple different ways of indexing into Pandas data frames. Before moving on to the next part, any questions about indexing? So whenever you want to do indexing, the first thing you should think about, do I want to retrieve my items based on numerical positions, or do I want to retrieve them using labels? If it's numerical indexes, I'll go for iloc. If it's labels, I'll go for loc. All right. Now comes the part where what I told you earlier was that we usually don't define data frames inside of our Python code. It's much more usual, it's much more common to read data from files. And Pandas has the multitude of ways in order to read data in. It has a function to read CSV files, read TSV files, read Excel files, read URLs, all kinds of data, read even binary data on your hard drive. So here, I have this data for Vancouver International Airport, weather data, and that's stored inside of a CSV file. And I'm going to read it using this pandas read_CSV, and here is the contents of that file. And this read.csv, just like most other reading functions in pandas, it receives a lot of parameters. And you're going to want to have a look at the parameters that these reading functions have, just to basically be aware what kind of options are available to you when reading files. Okay, I just remembered to show you something very useful inside of VS Code. So in VS Code, if you pull up this bottom panel over here, so the panel that I used for the terminal here, if I go to the Jupyter column variables, it actually shows you a list of the variables that are defined, and you can actually click on any one of them here. For example, if I click on S, it will open up a window here for me. And here I see the values inside of my data frame. I can actually filter them, explore the values in there. Let me see this one. So this is the data frame that I just imported. And you can see I have access to all of the values. This is a very convenient way of inspecting the values that I have defined inside of my VS Code. Instead of printing stuff all the time, you can just pull up this bottom panel, go for Jupyter variables, and there you go. All right. Let's go into Zen mode again. Okay, so you can also print it's not just for input, you can also use df.toCSV to write the data that you have in your Python environment to a CSV file. That option is also available. We also have the option of reading data from URLs online from the internet. If there's a data file, we can grab it directly instead of downloading it first. For example, this is the COVID data from WHO, and you can see that I read it just right from the internet. And that option is also available to us. There are also, again, a lot of other ways to read data into your Python environment using pandas. You can explore them in the pandas documentation. One important thing here is that, and that's something that comes up in the lab, is that you can, for example, import only specific columns inside of your data file. For example, that's one capability. You can change the column headers right away when you're importing those files. You can change the indexes right away when you're importing those files. And those are the kind of options available to us. So when you hover over this, you can see there's a lot of parameters. It's not very readable in VS Code like that, but if you refer to the documentation, you can see a much more readable list of parameters. Okay, yeah. Do you have a question? Okay, yeah. So let me just, before finishing, let's just go over a couple of common data frame methods over here, just to show you how they work. So here I'm reading the YVR data again, and then suppose that I want to take a sample of 10 rows at random. I can do df.sample and supply a number in here, and here I get back 10 rows, 25 columns of randomly sampled values. And you can see that they're random because their row indexes are just unordered. Okay, I can also compute the maximum values inside of each one of the columns. Again, this is something that could be very helpful to just quickly understand what's going on in my data set. df.max, I can also compute the maximum of one certain column, and that's by grabbing that column and then apply .max on that particular column. Because these methods are defined for series as well as for data frames. I can apply that onto the entire data frame or onto one series. idxmax returns to me the index of the maximum value. For example, here, the index of the maximum value in that column is 870. And if I want to confirm that, I can supply that 870 into my ilog function, and I can look at extra max temperature here, external maximum temperature here, and I can see that it's 34.4. That's the maximum value found in that column. Okay. And then same goes for df.mean. I can provide an axis along which I want to compute the means. I can compute the means along the columns or along the rows. And here I'm doing it along the rows. So I'm computing the mean for each column, basically. And we have also other helpful methods like sort values. I can sort the entire data frame based on a particular column. So here I'm sorting based on this maximum external temperature, and you can see that 34.4 is at the top, and then we have a sorted data frame based on that particular column. And notice this ascending equals false parameter. Okay, just another example. Once I have obtained my sorted data frame based on a particular column, I can chain a .log function to it in order to inspect it further. For example, this is the part that sorts my data frame, and then I can directly use .lock on it to further narrow down my search. Okay, and one last thing is that I can also sort a data frame based on the row indexes. So here I've taken a sample of 20 values. Because they're random, they're not going to have ordered indexes. And here, I'm applying sort index to say, hey, sort this particular data frame based on the row indices. All right, this part, categoricals, is optional. You don't have to read it, study it. It's not going to be on the quiz, but if you had time, it would probably be helpful to take a look at that. This is very much similar to the factors kind of variables that we have inside of R. And basically, what we can do with this is that instead of having data stored as cold, hot, warm as strings, we can save a lot of memory and gain a lot of performance by using the pandas categorical data type. And that tells Python that there are only these certain cases possible with this particular column. And one capability that it gives you is that it can be sorted, it can be ordered, and then pandas infers particular orders from the data that you have. You can perform certain comparisons with the data, even though it looks like being like string values. These kind of conditional operations are possible because they're categorical and they're ordered and they have special meaning associated with them. Okay, again, this part is optional, and yeah, looks like we are done with this lecture. So yeah, let's take one question. Oh, sure. So here? Okay.
So the bottom says you can specify order true to enforce the order that is in the categories list. Right?
Exactly, yeah. The order is inferred from that categories list over there. Yeah. All right. Okay, thank you everybody for attending today's lecture, and I'll see you in the lab today.